Hello friends, welcome to engineering tutorial. So in the previous video we discussed some of the basic concepts associated with electric dipole, and I told you that we'll be discussing about the electric field due to the electric dipole in two separate videos, one for the axial line and one for the equatorial line. So in this video we are going to discuss about the dipole field along the axial line. Okay, so before we discuss all that, let's just brush up a few concepts related to electric field so that there is no confusion about the various expressions, mathematical expressions that will be coming up. Okay, so the electric field, okay, at any point in space, because of a system of positive or negative charge on a positive test charge, is given by the following expression. Okay, so let us say that we have a system of positive charges and we have a positive test charge, a very small positive test charge at a certain distance away from it. Okay, now because both of them are positive charges, because it is a higher positive charge, large number of charges are present, and this is a small positive charge, therefore as both of them are positive there will be an electric force of repulsion. Now if this system of charges is negative, then there will be an electric force of attraction on this small positive test charge. Okay, so these two things are important. Now the electric field, because of this system of negative charge and positive charge, that is given by the electric force acting on the small positive test charge, regardless of the fact whether it is an attractive force or repulsive force, the magnitude of that force divided by the small positive charge itself. Okay, so the electric field is given by the electric force of attraction or repulsion on the small positive test charge divided by the test charge itself. Okay, so this is the scalar representation. As electric field is a vector, it has both magnitude and direction. Okay, because depending on the system of charges, whether it is a positive system of charges or negative system of charges, the direction of the force will be different. In this case it is electric force of repulsion, in this case it is an electric force of attraction. The directions are opposite, so in vector form it will be given as electric field E vector, okay, is equal to Fe vector by Q0. Same expression, just the vector symbol will come up. Okay, now discussing about the electric field on a dipole along the axial line. Okay, so here we have is the electric dipole. Okay, it is a combination of two equal magnitude charges but with opposite signs separated by a small distance. Okay, so here it is minus q plus q, separation distance is 2a. Now OA is equal to A, OB is equal to A. Okay, this point O is at equidistant point from A and B. Okay, now this line, dotted line here in the horizontal direction, this is the axial line. We have already discussed these things, so I would recommend you to please watch the previous video which I have posted, which is the electric dipole basic concepts. There I have discussed in detail about the electric dipole, the dipole moment, axial line, equatorial line, dipole field basics, all the things. So you please check out that video. Okay, so this is the axial line in the horizontal direction. Okay, now let us pick a point P here on the axial line, any random point we pick. Now the distance of this point from the center of the dipole, this point O, let's say that is x. Okay, now let us suppose a small positive test charge is present at P. Okay, a small positive test charge, let's say the test charge is given by Q0. Okay, small q subscript 0. It is present at P. So now we have to evaluate the electric field first by considering this charge minus q, then we will consider this charge plus q. Now I would suggest you that you please bring out your pen, paper, pencil, whatever, and you write down the mathematical expressions in a step-by-step manner as you watch this video. Okay, so that you follow the steps, you understand it in a better way. Okay, so please bring out your pen, paper, and you write down the mathematical expressions as you see it in this video. Okay, now a small positive test charge Q0 is present at P. Now the electric field at P is because of both the minus q charge and plus q charge. So first, the Coulombic force acting on this positive test charge due to this minus q charge, it will be given by F1 vector. This is the Coulomb's law, which is 1 by 4 pi epsilon 0. Okay, 1 by 4 pi epsilon 0, the product of the two charges, minus q, q0, and the separation distance between minus q and this test charge present at P. Okay, I have not written it here. It's just that you assume that this positive test charge Q0 is present at P. So as per Coulomb's law, it is directly proportional to the product of the two charges and is inversely proportional to the square of the distance. So this separation distance is AP, which is nothing but x plus A, OP plus OA, x plus A. The separation distance AP is x plus A. OA is equal to A. This point O is equidistant from A and B, and it has a value of A, and the point OP, okay, this distance OP is x. So the F1 vector, this force, is equal to 1 by 4 pi epsilon 0 q0 by x plus A whole square. Now this negative sign comes here because of this minus q charge. And another thing to note here is that this Coulombic force is of attractive nature, because here we have is a negative charge, here there is a positive test charge. The test charge is positive, so the Coulombic force because of minus q will be attractive in nature. It will be towards A, okay, in the direction PA, this Coulombic force. Now the electric field, from this definition which we just studied, the electric field is nothing but the Coulombic force divided by the test charge itself. So it will be the E1 vector, the electric field due to minus q is E1 vector is equal to F1 vector by q0. Okay, F1 vector is this. So this electric field due to minus q will be simply this expression F1 vector divided by q0. So q0 would get cancelled from the numerator and denominator, and it will simply be minus 1 by 4 pi epsilon 0 q by x plus A whole square. Okay, the electric field due to minus q, this portion is complete. Now if you have any doubt, any confusion, you pause the video, you rewind it and watch it again from the beginning, or from the point where the confusion starts in your mind. Okay, so again, this is the electric field due to minus q. It is an attractive electric field because the force of this force here, the Coulombic force, is attractive in nature because it is a minus q negative charge and it's a small positive test charge which is present at P. Now Similarly, okay, now again, the magnitude of the electric field is simply, we take out the minus sign, it will be simply be 1 by 4 pi epsilon 0 q by x plus a whole square. And the direction of the field, as it is attractive in nature, the force is attractive in nature, it is towards a, okay, in the direction pa. Okay, now the electric field due to plus q, this plus q charge present at b. Now here it is positive charge, here also the test charge located at P is positive. So the electric field E2 vector, okay, E2 vector due to plus Q will be a repulsive field because both of them are positive, like charges. So they will repel each other. It will be repulsive in nature. Okay, so it will try to push itself away. Because of minus q, there was an attractive force and the electric field E1 vector was in this direction. But due to plus q, okay, it will be the E2 vector, the electric field will be in this direction away from it, because it is both the charges plus q and the positive test charge at P, they are same in nature, they are positive, so they will repel each other. Okay, now the electric field due to this, similarly as we did for E1 vector, no need to go about the whole F2 vector and all that. So here the electric field will simply be 1 by 4 pi epsilon 0 q by bp square. Okay, we directly did this. Okay, we I skipped this part of f2 vector is equal to, here the only change will be f2 vector is equal to 1 by 4 pi epsilon 0 q0 by bp square, and here in place of x plus a there will be x minus a. Okay, x minus a. Okay, the distance bp is, this distance ob is a, from OP it is x, so simply BP will be OP minus OB will be x minus a, this separation distance BP. So F2 vector will simply be 1 by 4 pi epsilon 0 QQ0 by x minus a whole square. Here it will be, instead of AP it will be BP, and instead of minus there will be plus F2 vector. And E2 vector will simply be F2 vector divided by q0 divided by the test charge, and that will be this E2 vector. Here I have taken the modulus directly, which will be 1 by 4 pi epsilon 0 q by bp square, which is equal to 1 by 4 pi epsilon 0 q by x minus a whole square. Okay, and here, as it is repulsive in nature, this Coulombic force is repulsive in nature, it will be in this direction. Okay, away from P. Okay, along the along BP. So the direction of the electric field E1 vector and E2 vector are opposite in nature, because for minus Q the electric field, the Coulombic force is attractive in nature, that's why the electric field is along PA. But for plus Q the Coulombic force is repulsive in nature and the electric field is along BP, away from. Okay, so E1 vector and E2 vector are, now we have the expression. Now take a look at both the expressions of E1 vector and E2 vector. All the things are same, 1 by 4 pi epsilon 0, 1 by 4 pi epsilon 0, q in the numerator, q in the denominator. Here it is x plus a whole square, and here it is x minus a whole square. The only thing that is different. Okay, the directions are different, but in terms of the numerical, okay, the numbers thing, here it is x plus a whole square, which is a larger number, larger value, and here it is x minus a whole square, which is a smaller value. So any smaller value in the denominator will cause the value to go up. So naturally E2 vector will have a higher value. The magnitude of electric field due to plus q will be higher than that for minus q. E2 vector modulus will be greater than E1 vector modulus. Now the net electric field here, the net electric field is along the direction of E2. Okay, the net electric field E vector is along the direction E2 vector. Okay, the direction of the net electric field E and E2 vector are same. So as E2 is greater than E1, so this was taken. So the net resultant electric field will be E2 vector modulus minus E1 vector modulus, and it will be along BP, okay, in this direction towards the right hand side. Because E2 vector is greater than E1 vector, that's why this convention was taken. So this, if we do some mathematical simplification to it, it will be E vector is equal to 1 by 4 pi epsilon 0 q by x minus a whole square, which is E2 vector modulus, minus 1 by 4 pi epsilon 0 q by x plus a whole square, which is E1 vector modulus. Then we do the mathematical simplification. We took the LCM, okay, we multiplied x square minus a square whole square, and then we did the mathematical simplifications, which are basic mathematical simplifications, and we finally got the expression in this form. E vector modulus is equal to q by 4 pi epsilon 0 4ax by x square minus a square whole square. Now here we will make some slight modifications in the numerator so that it will come in a proper way. This expression will come in a proper manner. We will modify the numerator in this way. Q into 4ax, we'll write it as q into 2a into 2x. Okay, 2a into 2x is same as 4ax. So here we'll write it as q into 2a into 2x. Okay, so don't be confused that it is cross product. It is not. It's simple multiplication. Okay, it is not cross product. Okay, it is simple multiplication. So here q into 2a, we know that this is the dipole moment vector. P vector is equal to q into 2a. So we can write this expression as, okay, q into 2a, will substitute it with p vector, and it will become p vector into 2x by 4 pi epsilon 0 x square minus a square whole square. We simply substituted q into 2a with p vector. Okay, and the direction of the net electric field intensity, okay, at the point P is along BP, okay, along BP, in this direction towards the right hand side along BP. Okay, so this is the final expression. Now if the dipole is a very short electric dipole such that this condition is valid, that is, the length of the electric dipole, okay, this length of the electric dipole is much lesser than this x value. If this length 2a is much lesser than this, the distance of this point P from the center of the dipole, then we can neglect this a square because it will be a very small value, and it will simply be 2p vector by 4 pi epsilon 0 x cube, because it will become x square whole square will be x4, x will get cancelled, and it will become p vector 2p vector by 4 pi epsilon 0 x cube. Okay, so this condition is valid for only the short dipole, but this is the conventional mathematical expression of electric field intensity along the axial line of the electric dipole. Okay, so this is the whole mathematical derivation. So I would request you to please practice deriving this expression on your own, and at any point if you have any confusion, pause that at that moment, and again start from the point where you don't understand it, and write down the expressions as you watch this video. Okay, and practice this and it will come to you. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.